Hello everyone. Good evening.
Good evening, sir.
Yes, good evening. So in this session, we'll cover week 12, which has topics. So, earlier in week 11, we had attention. So now we'll have something called self-attention, and that leads to another similar function, but it's just called as cross attention, where we connect encoder with decoder thing. So that's called cross attention. We'll look at, and then something called mask attention. So we will see that also. So this three types of attention is there, but equation wise, all of them will be very similar to self attention. Um, just a little bit of changes in that. That's all. Okay. Uh, any any doubt you have before we start? Mhm. Okay then. So let's see. Okay. Well, we have to see what is self attention, and then other variants are going to be cross and masked attention. And then after that, we'll look at the what is decoder layer, right? So how decoder block looks like in this, right? So structure, architecture of decoder. Um, okay. So earlier we saw that in attention, uh, so the equation for that was, say, if you wanted to find score between st minus one and any hj. Uh, so let's say your or your sentences. I think say deep learning uh, course is good, something like that, right? So this sentence is there. Now this contains five tokens. As of now, we are calling tokens as individual words. Okay, so these are called tokens. Then HJ is any of this word you can take. So with respect to deep, you wanted to find of ST minus one. Um, then that score we are computing it. So this score you will get using multiplying with VT attention and 10H. We wanted to include some non-linearity, and then there will be U matrix, and uh, U matrix will multiply with ST minus one from there, and plus W uh, will multiply with HJ, and and that's all right. So I've excluded the bias term here. I mean, it could be there, but we are not including in our course, in our slides. Not this, I have excluded this, but bias could be there. Okay? If you see somewhere, it's the same thing. Now we have this things. Now, if I tell you the dimension of it, so P attention will have a dimension of uh, a single vector, right? So this is going to be like a just a vector, and U attention. So this U attention will have dimension of R D cross D, and W will have dimension of again D cross D, right? So D is the size of the embedding, right? So let's say D was the word. I produced an embedding of some vector size, right? So this vector size is of D. Right? So from here and I'm getting this. So this U and W are going to be square matrices and V is going to be vector. And if you compute all of this, you are going to get single output, right? So that is you can call as E or anything. E, in this case it is probably J T. So T is like any timestamp. So for each timestamp, you have to do this computation again and again, right? So first timestamp you have to do it for the decoder part I'm talking about. Then second uh, timestamp of decoder, you have to again calculate all of this and then come up with it. Right? So this as time changes, you have to do it. And this is for the first one. If J is one, J is two, then learning and for course is good. Right? So that's how you'll get five things. And finally, you are going to compute uh, a context vector. Right? So context vector is called CT. That is summation or first you're going to apply a softmax over this. So you'll have multiple this EJTs. Let's say E1T, E2T. In our case, it is still E5T. And on top of that, you're going to apply a softmax, which will give you alpha 1T, alpha 2T, alpha 3T, and so on. Right. So this alphas value you have HJs. So all of this something like this HJs will be there with you. From that, you can produce context vector, right? So context vector is nothing but multiplication of alphas with H, right? So whatever H J is and alpha J T, right? So this multiplication, if you do for all of them, you have to do, right? So whatever your sequence length is, for all of them, you have to do, okay? And you will get this. So this CT you are going to send it to RNN network, right? So this was the attention mechanism. But now we wanted to improve upon this. So what are the issues with this? That um, issues are that it relies on previous time step output, right? So it relies on ST minus one. So if I wanted to uh, do parallel computation, I can't do it. So for each time step, I have to wait for ST minus one uh, to come up, and then only I can do it. And another, yeah. So if I somehow able to produce, or if I somehow exclude this part and directly able to compute this vectors, for example, this multiplication vectors, then I'll be able to uh, uh, produce this attention fast, right? So we wanted to parallelize because if it get parallelized, then it will be faster. Okay? So um, so what we can do is we have, let's say, this embedding of my word. Let's say deep is the word here. Uh, this embedding for that, I can produce three uh, three vectors from this. One I'll call as key, another I'll call as queries, and third I'll call as value. Right. So these are vectors. As of now, I'm talking about vectors only. I think I can use small vectors only, but they are small. Okay, so uh, these are vectors as of now, which can have similar size or different size. Depends. It doesn't matter. But we can have this, right? And if I have this part, then what I can do is I can multiply k with sorry, I can uh, just so that's going to happen like now the equation will come up, but uh, yeah. So this is how I'll get deep, right? So now I wanted to find with respect to learning, like let's say learning how much attention deep is paying to learning, right? So that's what my target is. Now learning will also do same thing. It will also have some q something, right? So q, k, and uh, v. These are another one, right? So if I give a subscript, let's say one, this is two, right? So this three things I'll get from there, three things from here. Now I want to find the how much attention they are producing with each other, right? So how am I going to do that is uh, I'll do is I'll multiply, uh, let's say my deep is my query or something, then I'm going to multiply q1 with uh, k2, right? So q1 and k2, if I multiply that, and then I'm going to apply softness over it, right? So something like this if I do, then I'll get a value which will be attention weights, right? So exact equation of that is going to be like, if I we so, so the exact equation of that is going to be what we are going to do, and how we are going to do is, so first I have uh, so I have hj right here. This hj is there. Similar thing. Now I'm going to produce three vector out of it using metrics of WQ, WV, and WK. If I do that, I'll produce three vectors now, which I'm going to call Q, K, and V. Right? So Q, K, V are three vectors you are going to get out of that. Now, if you want to find the attention between them, what you can do is, instead of ST minus and 1 and HJ, which we used to do that, right? We used to do this. Now, instead of that, we can give Q1 and Kj, right? And they will multiply with each other and produce one single output, right? So, so you can think like this. What we are, if I give you idea what we are doing actually is, so you can assume something like, let's say we have a vector q1 and vector k1. If you wanted to find similarity score between, you might have done cosine similarity, in which what we do, we multiply q1 with k1, and then like kind of magnitude of q1 and k1, right? So that's how we can do similarity score. So same kind of idea was used here, that we wanted to find similarity between two words, how much they are similar to something. Based on that, we can get an attention score, right? So if I do that, I'll get even from that, and if I uh, and I'll have multiple even, right? So Q1 with K1, then K2, K3, K4, K5, whatever number of uh, words you have, or tokens you have uh, in your sentence, all of them will go through that. Then you are going to apply softmax over it, and then softmax will give you this, right? So again, now the same place where that we'll multiply each of this uh, attention score with vj here, right? So we produce uh, another factor called vj, right? So exactly this if we do, then this is called self attention. Now, to give you a better equation of this, the equation will look like something like this. So whatever we did, we produced q and k and v, right? Uh, and how did I get q? I multiplied my uh, vector with wq, right? So wq, if I multiply this, I'll get q vector, and if I do it for um, all the embeddings, right? So let's say I have 5 embeddings. If I do all of them, then I'll get a matrix out of it, right? So all of them vectors are now in a matrix, and that I'm calling as Q. Similarly, I'll have K matrix, V matrix, right? So this all now matrix in matrix form, and uh, you can see that now I don't need to rely on the previous timestamp also. Um, Something like similarity scoring I'm using here to get the scores out of it. That is the idea, and I'll do that. I'll multiply Q transpose with K, so that multiplication happens. It's like, you can think like, let's say I have first, second, third, and similarly I have uh, K. So this is Q and this is K, right? So how will I multiply my Q? So this is my Q1, right? Query one with E1. How will I do that? I have to transpose it, right? So if it is transposed, then this query 1 will become a row, and E1 will be a column, and then a multiplication will produce one output, right? So that one output is that. Similarly, Q1 will multiply with K2, K3, K4, and it will produce all of that. And then uh, you have to take softmax over it, right? So you have to take row wise softmax here, right? So just remember that the Q1 for each query you are going to find keys, and you are going to take softmax over it, right? So the softmax, that's how it is. So first row you'll take softmax, second row you'll take softmax, third row, fourth row, something like that, and all the terms will take softmax, right? So now something called so this term was introduced that what it was found that like I mentioned that what we are trying to actually achieve is something like called similarity scoring. Right? So two vectors are there, and we are doing something like uh, similarity scoring. So we have this vector multiplication here. Vector multiplication we are able to do. Now we are not dividing it with magnitude, right? So if I do that, then I might not need to scale it down. But this will give you a very high values, and this large values are not suitable for softmax. If softmax has any one large value, it will kind of blow up, right? So others will not get good score in this case. If we scale it down all of the values, then it will produce very good results. So that could be one reason. Another could be related to some variance and all. So if you divide this, then it will reduce the variance of the whole uh, whole matrix, and that also can lead to a good result, right? So so these are few ideas they come up with. So they use dimension of k. Uh, K is the one which we produced earlier, right? So this one is K, right? So whatever the dimension of this is that, let's say the 64 is there, right? T is the uh, number of tokens in this case, but whatever 64 is, you take square root of that, and you'll do that, right? So if you scale it down, then you'll get a good values. Then um, if you apply softness over that, you might be able to produce better attention weights without it, right? So that is that. And then final multiplication with v you are doing. So similarly, whatever you did as of now, that is the only thing you're doing. Alpha maybe j t you have, and then we are multiplying with all the vt. Right? So multiple v's you will have. You are going to multiply that, and uh, you'll get a vector where all the attention scores will be there, right? Um, so if you want to find the that's the parameters of this, then you can kind of think that this WQ is a parameter. So whatever total of that WQ matrix is most likely going to be D cross D, right? And similarly here also it's going to be D cross D, and here this is going to be D cross D. In this case, D is the size of the embedding, right? Whatever embedding size you can choose. So here they have choose 64 size embedding, and you can have that way, right? So now if you find the dimension of this, then um, uh, so Q will um, for that I think I need to solve this. So this is D cross D. In this case, D they took as 64, and there are T of them, right? So this is how much this I have D rows and T or capital T tokens. Then if I multiply, I'll get D cross T, right? So D cross T. In this case, 64 cross T. And similarly, I have same thing for K also, 64 cross T. Same thing I'll have here also, 64 cross T. Right? Now, if I multiply Q transpose and K, so this two will multiply, and it will produce T cross T matrix output. Then on T cross T matrix, row wise, I'll apply softmax. So it will not change anything. So again, you will have T cross T on the here as output. But finally, you are going to multiply with V transpose. It should be V. Yeah, okay. So it is V transpose. Okay, so it is not mentioned here, but it is going to be V transpose. Okay. If you do that, then you'll finally end up having T cross 64, right? So if you um, yeah, is it it is going to produce a T cross 64, right? So let's say you have started with T, then okay, finally you might end up with something different, but that is okay. Uh, okay, so that is self attention. What you have to do is you have to multiply the three matrices to produce key, key query and values vector that in some form, like this is the main idea of like how you are going to multiply. This is how you are going to multiply that. If you do this, then you will get attention scores. So this initial part, right, the softmax of that is called attention weights or score or alignment score, anything you can call, but that's what uh, attention is. Then finally, I'm going to multiply with VT, right? So VT have to multiply, and the final thing I'll get out of it. So Z1, Z2, Z3, and so on. Okay, fine. It's fine till now. To compensate, can you explain with the example of dimension? This one or previous one? This one will be right. Yeah. So this is the dimensions, right? Dimension of each of them are there. So you can see the dimension of, let's say, you can initialize dimension of W to as D cross D, some dimension. So that D will come from whatever embedding size you choose for this, right? So in this case, it was chosen as 64. So you can think of 64 cross 64. And then there are 64 uh, H1 and such T vectors are there. So that is going to produce this, right? So how many parameters you will have? Something like here you will have 64 cross 64, whatever value comes up, that many parameter, and into 3 you have to do for key and value also, right? So that many parameter you will have here. And is there any other parameter? No, there are no other parameters. That many parameters you will have, and this is how the dimension will be, right? So I have already explained that we'll multiply this, then we'll get the dimensions. Okay. Uh, now, okay. Now, what if we
So,
have
so one basic question, like you explained about WQ just now. Then WK and WV are also the parameters, right? In this case.
yes,
Okay.
yes, all three of them will going to be parameters.
Okay. Thanks.
Okay. So, so this up till this now it's a self attention. Now something called a multi-headed self attention or multi-headed attention only you can call that. So in this case, what you do, you have whatever you did just now. So this part, if you do it again for the embedding, same embeddings you have to take, but now weights will be different. So WQKV are going to be different, and you can initialize that. So that is called multi-headed attention, right? So you can see we have different this and different this. So you can kind of give a subscript to this. Okay. I will produce uh, something like this, right? So initial embedding could be similar. You can keep similar as of now. Okay, so just say that initial embeddings are same, but you use different matrices initialized different way, and then you did it, right. Now, why it will work or what is the motivation? Kind of you can think of from the CNN also that we apply multiple uh, convolution layers, right? So that we get multiple features. Now, some might extract edges of the image, some might take what is color changes in the image and so on, right? Some kind of feature it will extract. In similar way, we try to extract here what is the information in the token is there, or how token are related to each other, right? Let's say one token is related to other in a different way for one head, and in another head it is possible that they are related completely for different reasons. They are related to each other, right? So or you get different kind of attention score and the embedding. So finally you'll get the embeddings out of it, right? So you'll multiply with bt and you'll get embeddings out of it, right? So these embeddings are going to be a lot different in these cases, right? So that's why we can have this. Now that's called multi-headed attention. But if we do that, we have two heads. If we do that, and let's say if the first one produce, so here from this you can see the dimension of Z is going to be t cross 64, right? So let's say this is going to be t cross 64. This also produced t cross 64. And my initial dimension was 64. Here it was 64 um, cross t, and here also it was 64. It's the same thing I gave, right? Or you can think like I'm not having another 64 cross t, like it's going the same thing, or the same h is going there, right? So only 164 cross t I took, but I got my uh, embedding dimension got doubled, right? Now it is, if I concatenate them or if I add them, then it's okay. If I'm going to add them, then it is going to be t cross 64 only. But I'm not going to add. If I don't add, if I concatenate them, then it's going to be 2t cross 64, right? Which can be an issue. So what we can do is, um, okay. So yeah. So let's say if we concatenate, and that is what we are going to. We are not going to add them. Like h1 produce some output, some vectors, and h2 are some vectors. We are not going to add them. We're going to concatenate them. So concatenation is like whatever is uh, your vector is, you just put one beside other, right? Something like this. Now, in this case, the dimension got it it might increase, depends on how you choose the dimension of WQKB, right? So there is one another idea that you can initialize WQKB in such a way that it will produce uh, um, it will not produce T cross 64. So in this case, I'm just going to take T cross 64. It can produce T cross 32, right? So that is a way you can do that, and this will produce 3 cross 32, and you concatenate them and you will get finally t cross 64, right? So this is one way to do it. Another thing you can or even though we can have this, what uh, they decided is, okay, let's have this, I mean this way also, and another thing on top of that, we will add a linear layer on top of it, right? So we concatenate, we'll add a linear layer. So linear layer is like we are adding more weights to this. So weights will always help in learning, right? So we'll add more weights to this. So this learning will happen uh, after concatenation also, right? That's why this linear layer was introduced. So linear layer can do two tasks. One is it will learn something more than whatever this couldn't able to learn. Now, what is the concatenation representation is, or something like that, it is going to learn, right? And another is it will help you in reducing the dimension also. So let's say this t cross concatenation was t cross 600. You can have a linear layer in such a way. Let's say 600 cross 512 matrix. You can have this, right? So in linear layer, the weights is going to be there. We are going to call that as WO, and this matrix could look like this, and it will produce t cross 512 output, right? So something like that you can also achieve. So two reasons you can think. One is learning, and another is it will balance the dimension size after you multiply with it. Okay. Now, um, just to um, give you what how we are doing here, or what is going happening here is, let's say um, mentioned here. So Um, okay, so let's say we have 8 heads, right? So heads or H is 8. We have W, Q, K, V, and we are producing this. Now, what could be a size I can choose of W, Q is I can decide based on my embedding dimension. Let's say my embedding dimension was 512, right? So here it is D or embedding dimension or D is 512. If I multiply it with 8, I'll get something like um, I guess it is 64, right? I'm not wrong. Yes, it is 64, right? So I got 64 using that. Now what I will do is I'll produce output such I'll make my WQKV in such a way that I'll get an output here of size 64. Here I'll also get 64, and similarly for all the 8 of them, I'll get a 64, and then finally I'll concatenate them, and it will give me a size of 512, right? So that's how I'll do the concatenation, and of course I'll do the linear projection, one more linear projection over that, just to learn something new, right? So that's how the multi-head attention works. Whatever multiplication we did here, same thing we have to do. Just that the sizes or something you have to control here, so that your multiplication don't blow up. Um, that was the idea they used uh, uh, multi-headed self-attention. So uh, I mean, so what we are kind of changing is initially we gave all the weightage to 3 matrices where we are giving a D cross D matrix where we are using that. Now, if you use, let's say, D by uh, 8, yeah, so D by 8 cross D by 8, uh, or maybe D into D by 8 matrix, something like that, if you can use, then you can produce multiple of this matrices, and the multiplication will be different, and you will learn something new out of it, right? So how the learning new is going to be, you can maybe write a code of this and check what is first head is producing and what is second head is producing or something like that. But you will see that they are completely different representation of same embedding, right? So embeddings are going to represent in 8 different ways here. In this case, it's going to be 8 different ways. So what it will do is you wanted to capture the context of the sentence, right? What is the context of it? So maybe let's say this might be able to capture a context in some different way. This will capture the context in very different way, right? So that was the idea behind using multiple heads. And yes, so finally you will have multi-headed attention output, which is going to be embedding only. Okay. So just make sure that whatever goes from here, some D size uh, as a input, that much output you get here also. And so that is the idea behind it, that you get that, and you can pass it to the next whatever module comes. Okay. Uh, yeah, so this is concatenation, and then we are multiplying with WO. Uh, yeah, so each of them. Yeah. So that was there. Now we'll see another component um, of a encoder or decoder layer, which is feed forward network, right? So once you do the multi-headed attention computation, you can um, you can so next component going to come in the transform. So we are now into transformer, or we are looking into the transformer um, architecture. So where we have encoder decoder, same as earlier, encoder decoder only, but now we are calling them as transformer, which has one is MHA, multi-headed attention, and then second it's going to be uh, feed forward neural networks, FFN. This case. So this is just a simple version of that. Instead of self attention or just one attention head, you can have multiple heads. Right? So that's what this represents. Both are encoder only, but this is both of the way you can go ahead. But this is the way now people use it. Okay, this was just maybe initially they did it, but this was the best way to do it. Okay. Now, what is feed forward network is what whatever output you got from here. So you got output of T cross 512 size output, right? So T is the number of tokens. Just remember that number of tokens, right? Then you will have so this is the input layer, okay, or Z1. Then this is just a hidden layer and one output layer. Then this hidden layer, you will have some non-linearity here, but here there is it's just a linear layer. Okay, nothing there. Same thing was there with W also. There's no non-linearity, only linear layer, just weights, no sigmoid or tan H or anything. The exact equation of that is going to be we are using max of this. So if you remember, max is a ReLU function. This is kind of a ReLU function. That's what we are doing here. So this is a ReLU layer where W1 are the weights here. These are W1 weights, and this set is going to multiply. Some bias is there. Then now this is going to be W2, and for that also some bias B2, and yeah. So that's all that. So if you do that, then you will get a feed forward neural network output, right? So two components of um, architecture of encoder you have seen. One is multi-head attention, another is feed forward neural network. Now we are going to we are going to stack them, right? So one layer will have both of them. So um, it's there anywhere as shown. Yeah. So this is a encoder, or you can say this is the encoder layer one, right? So one layer contains multi-headed attention and feed forward network. Now we are going to stack the layers. So one layer on top of that six layer, two layer, three layer, six layer, right? So big models like let's say GPT and BERT and maybe T5 or something. So if you don't know this name, but GPT maybe Chat GPT. They've used this multiple layers, and they were able to figure out that it is able to learn better, right? So they started stacking up also. So that's why the computation of or computation cost to uh, to building this large language model is very high, right? It requires GPU for that because of this only. Okay. Now some calculation of parameters is there, but I guess I'll leave it up to you. You can do that. You can multiply the W, then WQ, W key, then W value factor. Then other parameters are going to be this feed forward neural network parameters that also you have to combine, and maybe bias also you have to add. If you do that, then it will be around 6.25 million parameters. So this many parameters are there only in the encoder layer itself. Now we haven't touched upon like decoder as of now, but that is also going to have almost similar number of parameters. Uh, I guess now we can see what is decoder layer. But is there any doubt in encoder layer? Okay. So in decoder layer, we have again the same thing, but uh, we have two different components. One is masked multi-head self-attention, another is multi-head cross-attention, right? So uh, self-attention is same thing. The cross-attention is something uh, maybe new coming up, and feed-forward neural network is what we have already looked at, right? So this part we know, but this two may be different, you can say. So let's look that now. Um, okay, so this next would be okay. So this is the next is let's say mass multi-head self-attention. Now, what happened is while encoder, you have the length of uh, what you want to encode, right? Let's say I enjoy the movie Transform. Now here we wanted to do uh, translation, right, in another language. So for translation, what is going to be the output of the what should be the output of the uh, output of this input, right? I gave something to translate. Now, what is the size of that going to be? I don't know. Most likely, uh, they are not going to be the same size. Right? Here it is of 5, but here it is only of 4. So it could come out to be anything, right? But what we can do is we can maybe decide some dimension that I'll allocate this much memory or some this much vector size uh, to be there by default, and it will produce based on that, right? So uh, if I do that, then there's another thing that I have to do is I can't take uh, uh, okay, so let's say I have four of them. Okay, four inputs are going in the decoder layer. These are from the, so we'll have X and Y pair, right? So X will have English and another is Tamil. Now Tamil have that sentence. Now that embeddings I'm going to send. Uh, Here X I'm going to send. I guess this is Y only, but in encoder I'm going to send X, and in decoder I'm going to send Y, right? So that's how it works. And Y, for Y, to the correct output I have to find, right? Maybe that correct output could be a different thing or something like that. So what I can do is I can say go, and rest of the word I can mask, right? So I have to mask the rest of the word because don't know what is the size it's going to take, right? Now some length I'm going to allocate, any length you can decide, t1 length I'm going to allocate, so all of them are going to be masked. Now if I compute this mask or this multi-head attention for all this mask, it will increase my computation cost. So to reduce this computation cost, what you can do, you just exclude this computation, and what you'll do, you will just compute whatever values you were able to figure it out, right? So let's say you sent a go, so that go is there, and rest of them you are going to ignore. um, and then let's say after some uh, yes, it is there, right? So let's say after some point you were able to figure out that the next is none, um, or at second timestamp you are going to, or second point you are going to send none, then that none, so up to two value you are going to compute the attention, and for third value we are going to only compute up to third, and so on, right? So at each point or each timestamp you are going to compute one one word attention, or whatever is the previous you were able to figure it out, right? So this much attention you are going to compute, but not rest of them, right? So multiplication will happen in such a way that initial words you choose, but not the rest of the words, right? Now few things you are not familiar with, which is how this is being used in, let's say, GPT or something. So something called causal language modeling will come up. But as of now, you think that uh, what we are doing is we are sending one word at a time. So we are sending go, and it will go up to full layer. Then it will produce something here, and with that, I'm going to feed here. Okay, or whatever the true word I know. If I do feature forcing, then I know the true word. I'm going to send that in next time step, or this two I'm going to send. It will again do it, and then while back propagation, it will come again here. Then third time I'm going to send it, right? So that's how I'm going to do here, one at a time. But for that, I need to do masking. So that masking is what called masked self attention. And how does mask look like? Something like this. So I'm going to mask it with minus infinity. So why I'm using minus infinity is because if you do the softmax, so one is q transpose k, this multiplication you have. In that you are going to multiply this masked one, right? So element wise multiply. So whatever the q transpose k size is, that is going to be t cross t, right? Same will be of size mask, right? Now if you compute row wise softmax, so what is going to be e power minus infinity? That is going to be 0. Okay? So if you have that, then it will not contribute at all to the softmax part, and we can remove this, right? So that's why we are using negative infinity uh, for that reason only. So that is the only difference between the self attention and mass attention. You mask the next words which you don't know, okay? Or you think you don't know and you mask them. But as you do back propagation and timestamp at one uh, timestamp, you give the next word, next word, next word. So rest of them you have to mask it, right? So masking is, that's how the masking is used. Okay. Now, okay, so that's how mask self attention is. Now we have to do cross attention. So cross attention is somewhere where encoder and decoder are going to meet for the first time, right? So something encoder is going to send, and uh, something decoder is going to send, and you have to kind of make sense out of it, right? So what encoder is going to send? It's going to send key and value vectors from here. So you're going to get key and values from the encoder, or just think that whatever, or just think that whatever embeddings you get from the encoder layer, right? So encoder layer will produce some embeddings. You are going to use that embedding and multiply with WQ, and similarly we are going to get key and value, key and value, right? So WK and WV you are going to multiply, which will give you the, the key matrix and value matrix. So key matrix and value matrix you are going to get from the encoder. Now decoder will give you query of this, right? So query will come from the decoder. So whatever you have computed mask, attention, and all will give you Q vector, a Q matrix out of this. Now again, you are going to compute the self attention. Same thing we did. Just it's just that we are going to get this thing from different perspectives. So you can kind of assume that um, we have keys and value from the encoder that we have learned, and now we have to search for what key can give me the result, right? So or what is the key for this query can give me the result. So you can think like that, and that's how the searching will going to happen using cross attention, and that cross attention then it will again produce the same output, right? So whatever dimension 512 cross t or something like that, and then you have to pass it to feed forward neural network. So uh, yes, so same thing they have done, and then finally you are going to pass all of this using through another linear layer, and then a softmax thing, right? So you can think that it's just a softmax layer, right? So softmax layer, something like this, with pre-activation of linear and then softmax of activation layer. So if you do that, then it will produce a probability of uh, of the words, and you can compute the loss, and loss you can bring back and do the back propagation, right? So update. So all of these weights which you are seeing on the screen, like WD here, some W1 and W2 will be there. B1, B2 will also be there, and here in this case it is some WQKV, QK and V are going to be there. So just make sure that here in cross attention there is going to be one head only. Okay, so here will not have WO. WO will not be there. Just QKV. Uh, yes. Um, wait, I think maybe okay. Maybe O is going to be there. I think it's mentioned there. I don't see a reason to do that, but okay, fine. So we can have multiple heads here also, and we'll have multiple heads here also. This is just a masking. They are representing masking here. Um, that how masking will be look like. So this masked attention. So here also again you have to update all the weights here, right? So W, Q, K, V, O for this part. So this four um, layers are there, four places are there where parameters are introduced, and that should be learned here, right? So in this way you learn here. Now we haven't gone into embedding, but there also all this uh, QKV and this W1, W2 will be there. That also will get updated, right? So there are many parameters in this, and all of them will get updated using backward operation. Okay, so position embedding on encoding is not there for our course, but up to this Up till this part we have in our ticket. Any questions on this?
So here, WK and WV are coming directly from the encoder, right? We are not calculating any. There are no parameters for decoder, right? Specifically.
No, they WK. No, W's are not coming from the encoder. Embedding is coming from the encoder. Right? So
Oh,
uh,
okay, okay, okay. Fine.
this the metrics you have to initiate here, and then you have to update it later.
So it will have its separate weights for even K and V as well.
Yes.
Okay.
Yes, yes. But the out or the multiplication of this vector, right? The embeddings
Mm-hmm.
are coming from this only, from the
Okay.
encoder.
Okay. Thanks.
Uh, right. So there's one thing in this, that how multi-head attention can compute. So let's say you have a sequence length of t, and you have number of heads, some h you have, and embedding dimension is determined with d model. Then your input will become t model cross t, right? So uh, it's like it's like one of d model, then another d model, similar, right? So d model cross t, right? So this is my input. Now wq uh, or wk or dkq, how will you decide? Mostly you can divide d model by h. That's how you'll get this k and q. Um, and there are no choice here, but dv you can choose, right? So anything you can choose, any value you can choose, but for k and q you don't have much choice here. You have to go with this if you're multi-head, right? So this is multi-head I'm talking about. For single head you don't have to do this, right? Now if you do this, then you'll get some dq, right? Some value, and cross d model, that is the size of wq going to be. Similarly wk will have another matrix, and wv is also matrix, and wo finally will be something like d model cross um, as many heads you have multiplied by dv, whatever dv you have chosen. So another matrix will get as wo, right? Now if sizes of dv you choose as different, so it's up to you to choose. Generally nobody does that, but if you do it, possibility does exist. Then um, then then you will not multiply, but you will add uh, each dimension, and that's how you'll produce the wo. Okay. uh, so let if I show you the multiplication of, let's say, wq with x, if you do, then you'll get matrix of t cross t. Here you get t k cross t, dv cross t, and final this q transpose k multiplication will produce t cross t matrix. Okay. And if you do multiplication vt, you'll get t cross dv. Now multiple heads will produce same thing, t cross dv1, t cross dv2. You are going to concatenate them. So you can see why we are getting this t cross h into dv. Or if if it was different, then you could have added all of them. Okay. Then finally we are having this wo that we are multiplying with whatever you got here, right? So earlier this z, uh, whatever you got, you are going to multiply that, and that's what multi-head attention is. To give you an example numerically, so let's say I'm choosing a sequence length of two, and number of heads are also two. Okay, so two heads I'm choosing, and d model is four. So you can see the dimension of embedding is four, right? So I, as of now, I choose some random number for embedding, but uh, what you generally do is you learn, or you create this embedding by learning subject. So let's say any embedding technique you can use to produce this, right? Um, SIBO or anything that is up to you. So yeah, so X is that. Now I have to definitely choose D and DQ like this. So it should be of dimension two. So and DB I'm choosing again two, right? So it's up to you. I said, but still I'm choosing two here. Now, how will you create WQKV? So let's say I have chosen or I have used same metrics for WQKV, or it's like three metrics are there, but they all have same values. Okay, just they are not. I'm not using same metrics to do the multiplication. I have three different metrics. It's just that they all contain same values. Okay, that's what I've done here, and I'm producing like my dimension, right? So how will I define dimension? So uh, R of DQ, which is this 2 and 2 cross 4. Okay. So that's how I'm producing this. These are also initialized randomly. As of now, we are randomly initializing it. It will, by back propagation, we have to update it, but will not go till there. It is very complex procedure, so we are not going to back of this, but at least we'll see what is going to happen in forward pass, right? Now, similarly, I have another head, second head, and that is also going to have same dimension. Again, three matrices are there, different three matrices. Okay. Then again, I have the last thing, which is output, and the dimension I have to choose based on this. The D model cross H 2 and DB also 2, right? So that is 24 cross 4. D model is 4. That's all. Now I'm multiplying it. QKV. Since my matrix is same initially, that's why I'm going to get same value for all three of them. I have to do Q transpose K. So I'm going to take a transpose of this, but you can see the transpose is taken, but since it's a symmetric matrix, so you can't see that, but it is a transposed one. Okay, if it's not symmetric, then you might be able to see it. So it will produce something like this value. Then you have to apply softmax over it, right? So softmax, I'm using the row wise softmax. So P, Q are there. For that, I'm taking softmax, and then R, S are there, and for that also I'm taking softmax. Okay. Which will give you something like this value, 0101. That is attention weights. So as of now, we have computed weights only. We have to do final thing, which is multiplied with VT to get one head output, right? So this is the output of my first head, right? So we have two heads. First head output this matrix 4848. Okay. Now similar thing I'll do for the second head. Whatever I did, same thing I'm going to do for the second head, and it's going to so it has produced this as output. So this is my second head output. Okay, H2. Now I have to concatenate them. So remember, I have to concatenate this. This is how I'm going to concatenate uh, sidewise, right? So head one and head two. So I'm concatenating sideways. I'm not concatenating in vertically, but horizontally. Uh, why I have to do? Because if you see the dimensions of this, you'll understand why I have to do this way only and not other way. Okay. Then the final thing I have to do, which is with WO, I have to multiply. If you do this, then you'll get this as output. Right? So this matrix multiplication I'm not explaining, but each element what is arithmetic, but you can assume that the calculation is correct. Okay. And yes, that's all is there. So this is how you will compute the multi-head attention. Now, if there is going to be mass attention or cross attention, something like that, if it's going to be cross attention, then uh, yeah. Yeah. So this cross attention, I'm getting one X from the decoder. I'll get another X, and you can assume X2 or something from encoder. Okay. Of same dimension, I'll get from encoder also same dimension. And from this, I'm going to produce key and value. From this, I'm going to produce query. Okay, or a Q matrix. Capital Q is capital K and capital V. Okay, so this three I'll produce, and then I'll go ahead. Right? So uh, this part I'll use for encoder. This two I'll use for decoder, and then I'll have those kind of matrices. Right. So I'll have different. This matrix will be different based on that, and then I'll do the same multiplication, and I'll go again for multi heads, and then I'll produce the output for cross attention. If it is going to be masked attention, so let's say I'm masking I'm sending first one, but I'm masking other one. Then how will I do that is I so this calculation will go on, right? So nothing will change here. WQ, be something like that you can think. But where I'm going to mask, I'm going to mask when I'll reach the softmax. Right? So softmax, inside the softmax, I have to mask this, where I'm not going to compute the the next layer, right? So the next one is this one in here. If you do the comparison, you realize that the peak, right? So this is for the first one. I'm doing it. That's why I get output here. For second one, I can't send this. So for this, I have to multiply with a mask here inside this. Uh, QK transpose will multiply with a mask of negative infinity, negative infinity. Okay? Uh, yeah. So mask you have to assume how it is going to be. I guess it is something zero and the negative infinity and zero something like that. Yeah, zero zero, right? So this is how my mask will be. So first timestamp this, but at second it will produce that, right? So that's how you'll get output for mask. I think. Yeah. So that's all I have. If you have any question, you can ask.
Sir, where do we
Yes.
get this PDF, sir?
It's there. We have to. I will upload it the slides.
Okay, sir. We will only get like this numericals in last week or in year, right?
Uh, no, I can't tell you that. Could be anything. It could be different. No, see, here we are using numbers, but there could be chance that you might get only uh, what you call alphabets or some variables. So that is possible. Let's say this is 2 and this is T, this is 2T, this is 4T. Anything is possible.
Got it. Sir, these formulas will not be provided, right?
It will be provided.
Okay, everything. Okay.
Anything else?
Sure, this week was good, but I need a like query recording the preparation for the end term, like how to deal with the paper, any strategy of revision.
Uh, so strategy, you have to focus more on the last 4 weeks, then the subsequent weeks a little. But so you should at least have idea of the primary architecture, which are ANN, CNN, and in previous weeks, and then RNN you should be RNN and this attention or multi-head attention, whatever is there in the 9 to 12 week, uh, you should be comfortable with that. Uh, yeah, so rest is you can
Yeah,
uh,
yeah, that's good, sir. Like Like we need to be more strong on the theoretical or problematic, so that we should more practice on the problematic things, or we should be strong on the theoretical thing.
More problematic thing. I guess. I mean, we. I mean, you have seen the quiz papers. We don't go much into theoretical thing, but mostly numerical questions will be there, right?
Yeah, sir. Like some quiz covers like theoretical and quiz to quiz one. So that we need to prepare more practice on the problematic. Okay, sir. Got it.
Share the link of the um, slide which I'm showing you right now. But as of now, I'll add into the calendar, so it is there, but it will be uploaded in the slides. Okay, so to see calendar some point, you'll have the slides.
Sir, upcoming session on the next Friday will be on a revision session, sir.
Yes, that is going to be revision. We'll have probably another also revision session before that.
Oh, pretty good, sir. Like covering which week, sir?
So maybe 9, 10th in next week, and then 11, 12th in the last session. Or we'll keep last session. So we'll have questions from like whatever questions you have doubt session also in similar sessions, right? So if you have any doubts from previous weeks or anything, you can cover that. But for revision session, you can watch whatever previous revision sessions happened for quiz 1, quiz 2 for the previous content.
Yeah, sir. That will be pretty good. Yeah.
Okay then. Is there anything else? So I uploaded the slides link in the calendar, and that with that anywhere you can take it. You have to, so uploading on the portal will take something. Okay, then is there anything else? Okay, then thank you everyone. We can close the session.
Sir, I have one doubt.
Yes.
Sir, can you scroll up a little bit in this slide?
Okay.
Yeah. So in this thing, head 2, you have calculated the attention rate. You multiplied the softmax into
To
that
V.
V rate. So,
Yes, V.
like, which, yeah, actually, you are telling Q2, K2, V2, right?
This is the second head.
No. Yeah, no. First line you have mentioned Q2, comma, K2, comma, V2, right?
Yes.
So, what is it corresponds to? Is it the matrix itself you are telling? Or?
Yes. So yes, sir. So how will you compute Q2, K2 bit, right? So you have this is WQ and this is the input X, right? It will
Okay.
give you Q metrics. Now, so what I have done is I have used same metrics or weights for WK also and WV also, right? So it would give you same output. So that's why I'm showing it this way, QKV. I mean,
Okay.
the
Everything is
computation
equal,
is
you
same.
mentioned.
That's why.
Okay.
Yeah. Calculation is
Okay.
same. That's why it is like this. But they all are different metrics. In reality, they all are different. Uh, and the updation will happen differently for all three of them.
Yeah. Only this example choose it correctly so that we got everything to right dimension. Yeah.
Yes. So that so see, matrix multiplication is not a part of. I mean, it's not a complicated thing. What we have to understand, how the architecture is happening, right? Or what multiplication is happening of all of them. So that's why to keep matrix multiplication easy, I'm using the same matrix.
Okay, okay. So it will be mentioned what would be the DV itself, right?
Yes, each matrix will be given to you, depend on the question.
Okay, sir.
Okay, anything else?
No, sir.
Okay,
Thank you, sir.
then.
Thanks for the information.
Okay, yeah. Thank you everyone for joining. We can close the session, right? Yeah. Bye.
Thank you, sir.